Hi everyone, welcome back to Coding with Bharat channel. So as you know, we are discussing DQ as the topic for this week, and today we are going to start a new problem on it, which is this constrained subsequence sum problem. So question simply says, let's say we are given an array, right? So we are given an array like this. We would like to form a subsequence out of it with maximum sum, right? But there is an additional condition. The two elements that we take together in a subsequence, they should at max be at k distance, right? So as an example, if I start with this 10 and let's say I'll take this 2, then I have to take at least one element in the next k distance, right? So the next element that I select cannot directly be 20 because then 20 minus 2, the distance would be 3, which is not allowed. Like it has to be within distance of k. So I'll take this 5 and I'll finally take this 20. So this is the sum that I'll get. Okay. Another case, subsequence we want to take. It cannot be empty, but it can be just one element, which is minus 1. So I can just take minus 1 and let it be over with. Next, this particular case, k is 2. So I'll take this 10. I could have stopped here, right, and not take anything. But I want to keep that 20 because that 20 is like a huge number which gets added. So I'll have to take some element from the middle. So one idea could be to take this minus 10, but then the sum would be like decreased a lot. So better is to choose this minus 2 and minus 5. So I'll go 10 minus 2, then minus 5, then 20. Right? I cannot directly go from 10 to 20 because the distance would be more than k. So that is what the question talks about. You have to find that subsequence which gives you the maximum sum. Okay. The first and most basic idea that many people would start with here is that taking positive elements is a good idea and taking negative elements is a bad idea and should only take it when there is no other choice, right? This could be a simple thing that might come to your mind, that let's always try to take all the positives, and then if we have to take some negatives, we'll take it, right? But this idea fails with a lot of edge cases, right? Like if you go into that route, you'll be facing a lot of challenges. So I'll give a few examples just to illustrate that. So let's say we have something like k equal to 3. So we have to take something in next 3. Let's say I have this. Now if I decide to take both the positive numbers, let's take this as 16. No matter what I do, I'll be landing into a sum smaller than 16. Why? Because if I choose minus 4, minus 5, minus 6, any of them with 3, because I cannot jump directly from 3 to 16. So if I take something in the middle, that will reduce the sum to a negative value, and that I'll be taking out from 16. So better idea than that is to just take 16. Just take 16 and be good and over with. Whereas if I take a 5 here, suddenly this changes to taking 5 minus 4 and 16, because now I'll be adding one more. When I do 5 minus 4, I'll be adding one more to 16, making it 17. Okay. Another thing, is it always a good idea to take the least negative number? Let's think about that. So let's say if I go back to this case, let's add a minus 1 here. Now, common sense would say that okay, if we have to take negative, let's try to take the least negative, right? So I'm talking about all the greedy scenarios that might come to your mind. But if you take this minus 1 here, again you will not be able to reach 16. So why to take this minus 1? We'll directly go to this minus 4 and then take 16. So similar to this, there could be a lot of cases. I'm not saying that there will not be a greedy approach. There can be a greedy approach, but that greedy approach will be very complicated to write. Like it will have a lot of if else, and you'll be stuck into the casework. So better, let's think about brute force in the terms of what subsequence tells us to. So whenever we are dealing with subsequences, we can go for take or leave approach. That is, at each index we can decide whether we want to take it or we want to leave it, right? So as an example, if I have something like this, let's say case 3, when I'm at 2, I'll make a decision. Should I take 2 or should I leave 2? So I decide to take 2 and I decide to leave 2. Now, if I decide to take 2, that means I have to take one more element till 2 plus 3, which is, 0 plus 3, which is index number 3. So till here, I would need to take one more element at least. So yeah, I can keep on passing down that, okay, till where I want to keep an element, and using that I can make recursive calls, right? So in this scenario, if you think, you can actually go for take or leave approach, and the time complexity when we write such a recursion is 2 to the power n, right? Because for every place we are having two options, either to take or to leave, right? So you have not dealt with recursion a lot. Feel free to not actually implement it, but I hope the idea is clear that we have two options at every place, either to take or to leave. Okay. Another simpler way to visualize brute force here is to think about this idea. Let's pay close attention to it. Okay. So when I am at the first element, right, there is 2. So I will take it. So I'll keep it like 2. Okay. So at every index, what I'm trying to tell is I'm trying to calculate what is the best sum that we can get when we take this as the last element. So if we take 2 as the last element, we'll get sum as 2 itself. Okay, let's go to 1, minus 1. So if we take minus 1 as last element in our subsequence, we have two options. Either to not take anything from the past, or take this 2 and add this minus 1 to it, right? So best case is to add that 2 into the answer. So I'll go with 1 here. The best sum that we can get taking minus 1 in and ending at minus 1 is 1 when we take both 2 and minus 1. Let's go to minus 4. If I want to take this minus 4, k is 3. So I can take this after nothing. So directly take this minus 4, or one step back, or two step back, or three step back. So if I take it after one step back, my answer will become 1 plus minus 4, which is minus 3. If I take it two step back directly after 2, then the answer will become 2 plus minus 4, which is minus 2. If I take it directly, the answer will become minus 4. So best that I'm getting is taking this minus 4 after 2. So I'll get my answer as minus 2. Next we are at minus 5. Again do the same logic. So minus 5 you can take independently. Answer is minus 5. You can take it after the previous one. Answer will be minus 2 plus minus 5 minus 7, which is again bad. You can take it after minus 1 directly, right? After this, in that case, the answer will be 1 plus minus 5, which is minus 4. Last scenario, you can take it after 2. So 2 plus minus 5, which is minus 3. So best answer we are getting is minus 3 out of all of this. So in a way, what we are doing it to calculate the answer at any position. What are we doing? We are going over the previous k elements, and taking the maximum out of it. Also taking max with the current element. So max with the current element and the previous k elements. So minus 5 versus minus 2 plus minus 5, 1 plus minus 5, and 2 plus minus 5. So the best out of this is 2 plus minus 5, which is minus 3. Let's go to this 3. So either 3 plus 0, 0 is one option, minus 3, minus 2, 1. So best is to take this 1, and I'll go 3 plus 1, 4. So can you see? For getting to 3, the best answer is 3 minus 1 and 2, right? Not taking minus 4. But now when we go to the 6, the best answer to reach this 6 is to take 6 plus, options are 0 or the previous 3. So out of the previous 3, I'll take this 4. 6 plus 4, 10. So the best answer that you can see is that we can get is 10. By ending at this 6, we can take 6, 3, then minus 1 and then 2. Okay. If the answer always going to be the last one, answer is no. Like if there is, let's say, a minus 7 here, what will I do? Minus 7 plus maximum of the last 3. So maximum of the last 3 is 10. So minus 7 plus 10, which is 3. So the answer is not this 3, but this 10, because still we will end at this 6. We can end anywhere, right? Any subsequence can end anywhere. So basically what we are doing is, if I talk about in terms of code, for every element for I equal to 0 to n minus 1, what I'm doing is I'm calculating the maximum answer that we have got for the previous k elements. So what I'll do, I'll declare a maximum as 0 and I'll go over j equal to I minus 1 to j equal to I minus k. I minus 1 to I minus k. Find the maximum and put it into this maxi variable. So maxi equal to max of maxi. Let me adjust my screen, comma, answer of j, right? So take the maximum of all the answers and 0. 0 we have already taken here. Out of these, whatever maximum we get, the answer for the current place is nums of I plus this maxi. So I'll say directly, answer of this I is maxi plus nums of I, right? So basically for every element, calculate max of the last k answers and add the current answer to it. Okay. So this approach is kind of like DP. This is a 2D DP scenario, right? As it's a hard problem, obviously, it will not just be one simple technique. It would be combination of a few. So this approach that we are doing is very similar to a longest increasing subsequence kind of DP, right? What do we do in longest increasing subsequence also? That for any element, we try to look back for what all elements we can make this as the next element and calculate the result for it. Same thing we are doing here. For every element, to calculate the result, I'm going back, going to all the elements with which I can put this as the next element and finding the best out of it, right? So this is again a common pattern. Probably will take up in one or more coming weeks this particular pattern as well, right? So this idea, if you think about it, takes the time complexity of n into k, because for each element to calculate, you are going over k elements in the past. Okay. But if you look at the question, this problem that we have been dealing with, n into k will in fact be a problem. N and k can be 10 to the power 5, so we'll end up having TLE. Last step, to optimize it. Optimize it, what we can do? If we think about it, this portion that we are doing, finding the max, is nothing but maximum of the last window of size k. And when we move to the next element, we are kind of shifting our window one step forward, right? So if I go to the answer array, when we are calculating the result for this 3, we were taking maximum of these 3. Now, when we are calculating the result for the next element, which is 6, we remove this from the window and add this to the window and want to find the max. So if you think about it, this is nothing but the sliding window maximum that we can easily solve with DQ. So if you remember, what did we used to do in DQ? We whatever element has been moved out of the window, we will remove it. The new element that comes into the picture, first we will remove the useless elements from the back and then push our current element. So that we have already discussed in the previous video, just the previous video on the channel. So you can go check it out, or the previous video of the playlist as well. Cool then. So basically with the help of sliding window, we can ensure that our O of k factor which was there is gone, because now we are not doing n into k to find the sliding window max, but we are sliding the window with this O of n itself, right? So yeah, let's go into the coding part of it. Okay. So what I've done, I have declared DQ, right? So I have not declared two different arrays for answer and nums. What I'm doing is, when I'm calculating a result for an answer, I am just replacing it, right? So for example, if here what I was doing is I was creating a separate array. Now I am just replacing in the previous array because previous elements are no longer required. So I've avoided taking an extra space of on by creating a new array. Okay. Like total space is still O of n because we have the DQ as well. So I'm not saying that total space is O1. It's okay actually, because at max k elements would be there in the double-ended queue. But we have avoided creating an extra answer array by replacing the old array itself. So yeah, let's get into the code. So what I've done, I've declared this double-ended queue. Now, every time what do I do? For every element, I first calculate the result for the current element. How do I do that? I would need to take the maximum of the previous k, which are stored in my DQ, right? So in my DQ contains the last k elements max, and then yeah, just store it in nums of I, right? Okay. Next, what I'm doing is I am inserting the current element into the double-ended queue. So current element I'll insert into the double-ended queue. Lastly, I will look into both of these functions in a while. But yeah, these are the two steps, right? That calculate the result for the current element, insert the current element into the queue. Okay. Lastly, what I've done is I have taken and returned the maximum element that we get into the nums array, because we'll have answer ending at each position. So we want to take the maximum out of it. Okay. Let's look at the get best and the monotonic insert function. So let's first look at get best. So we have some elements in my DQ. I want to take the max. So if you remember, we made sure that this DQ is maintained in monotonic fashion, right? So let me first probably go to the monotonic insert to like re-establish that fact, that how do we get the elements in monotonic decreasing order, like the max element at the beginning, then less, then less, then less, and so on and so forth. So what I'm doing is, till what I see, the element at the back, so element that is at the end, which is supposed to be the smallest element, if that is less than the element that I'm trying to insert the index. So if nums of index, that is the element that I'm trying to insert, is more than the element at the back, remove those elements from the back, pop back. Then take the current element and push it at the back. So this will make sure that the elements which are smaller and come before, they are kind of removed from the queue because they are useless. This new element will always be more than the previous. So previous ones are kind of useless now, right? So that is the idea of uh, sliding window max that we discussed in the previous problem as well. So okay, so main point, queue is maintained in monotonic order. In get best, what I'll do is, if I see that the element at the front is at more distance from index than k. So if we see that the index for which we are trying to get the answer, if for that index the element at the front is having more distance than k, then I'll remove that element because that is no longer required. We'll just be calculating an answer for the future, and that element is now useless because the window has moved out, or we have slided out this particular element. Okay. So this is for removing the initial elements. Now, okay, this I think is a mistake. We can ignore this. Now what I'm saying is, if my queue is not empty and we have some element in the front and that is positive, that means the maximum of the previous is positive element. So I will take that element and add numsI to it. So I will return whatever is in the front plus the current element. If my queue is empty, that means there is no maximum element right now, like it's the beginning. Or if the maximum element itself is negative, then why would you want to add it? So you'll take the current element itself. So you'll say return nums of index. Remember, this is not, nums doesn't have the exact values of the original array, but they are transformed values. So I'm not saying that negative elements will be ignored. I'm saying the answers which are negative, why would you want to take that? Because adding that to the current element will bring down the answer further. We'll take instead 0, which is not take all of them and just move ahead with this particular element. Okay, so yeah, that is how this particular code is written, where for every element we are first calculating the best results and then we are doing this monotonic insert. Again, it might look like inside the for loop we are doing two while loops. So it is supposed to be n into k or n square or whatever. But actually, if you think about it, every element will get pushed into the queue once and will be removed also once, either from the front or from the back. So actually, the number of times these two while loop will run in total is just equal to total number of elements. So at the end of the day, it can never happen that we are going over the element n times to make it n square, but for every element we'll just be going it once inserting it into queue and once removing it from the queue. Cool then. So this is about this particular problem, constraint subsequence sum. Do give it a try. I'll put the link also in the description. Do like the video if you did understand the solution, and share it with your friends, and do subscribe to the channel if you're new here. Let's see you guys tomorrow. We'll take up one more problem on this particular pattern of DQ.